Okay, welcome back to another edition of Organic Chemistry. We had previously looked at various different interconversions between acid derivatives. How do we turn acyl chlorides into anhydrides, esters, amides, what have you? How do we turn anhydrides into esters and amides? How do we turn esters into amides, and so on and so forth? So we're going to continue that by looking at other reactions, and maybe we'll get into individual components. So let's start with adduction of acid derivatives. That essentially, we can get one way to it. Breaking this down, from our acid, okay, let's see if this is actually any better. From our acid, our anhydride, our ester, all those, when they get converted, when they get reduced, will go to a primary alcohol. All those will be converted to a primary alcohol. Yeah, so acyl chlorides. So all those can be reduced to a primary alcohol. Remember, we have a lot of different reductants. Lithium aluminum hydride is the strongest. Sodium borohydride is a little bit weaker. And we can get even weaker by adding on various non-reactive functional groups onto there to increase the bulk and remove the hydrides. So, but the general reaction with lithium aluminum hydride is as follows. Draw by hand, because otherwise it doesn't look like it's crappy, but still it's a lot better than trying to draw by mouse. So let's do like an ester. So you'd add 2 equivalents of lithium aluminum hydride. So the first one's going to be producing RCH2O minus lithium plus, and then the R prime O lithium plus. And then in the presence of acid or water, basically a stronger acid than we got, we're going to form our 2 alcohols. Now, sodium borohydride being weaker, will work only on acyl chloride. So if I can do that with acyl chloride, essentially with sodium borohydride, we're going to have our primary alcohol and our 1 and then 2. H2OH, and then of course NaCl. But now, I mean, the sodium borohydride with acyl chlorides will, most of these guys will essentially go through an aldehyde intermediate. But in order to stop the aldehyde, we need an even milder reductant than sodium borohydride. So, for example, we can use something like lithium triterbutoxide aluminum hydride. So, like, as I said, these guys, there's various different versions for various different things, but essentially we have one hydride atom, and the other functional groups is O butoxide. The idea is that these guys are very sterically bulky, so as they bind, as they drop the hydride, they can bind to the oxide part of that, and they keep from over adding. Then they're replaced with water. So essentially, this way we can turn acyl chlorides and ether, solvent, we can essentially get this to an aldehyde and stop at just an aldehyde. Esters and nitriles can also be stopped at aldehydes with slightly different reagents, but this was covered in previous esters and nitriles. But this was covered in chapter 18, but I'll refresh these real quick. So these be like this is aluminum hydride, isobutyl, and low temperatures. Low temperatures. Where isobutyl would be 1, 2, 3, 4. So from this way, we can go from an ester to very low temperatures, 98 degrees C. There, aluminum hydride. Essentially, what we're going to go through is an intermediate that looks like this. H O prime O. And then what we see is then the loss that when we add water, the loss of this, and we kick off the functional group. We pronate there, pronate the ester, pronate the essentially the alkoxy group, and kick off the aluminum, and we form our aldehyde. The OH can go there, proton can go there. We can do the same thing with nitriles. Let's see. Now, amides, if we reduce amides by lithium aluminum hydride. We can also reduce nitriles in the same way to primary amines. So amide, so depending on the conditions, amides / nitriles can go to primary amines by just using our standard lithium aluminum hydride. Overpower this, not try to do anything else. So essentially we're going, we're going to go C double bond O, NH2. Step 1, lithium aluminum hydride. Step 2, water. Remember, we always add this in two different steps. Otherwise, the water will deactivate the lithium aluminum hydride. Two. Now, the mechanism here is that nitrogen is a weaker leaving group than the aluminum oxyhydride. And so as we're looking at this, making a stronger leaving group for the oxygen. So like essentially here, let's look at this. R, C. So we have aluminum, let's put H3. We're attacking here, kicking that up. Form our O minus H2. Now this can attack our aluminum hydride plus to form R, let's see, H2, H, and H. Now from here, this can donate the lone pair in, it's kicking that off, so that we form our, so to say that the amine is the weaker leaving group. So we'd much rather have forming imine and O, L, 2. And from there, the last step is we have another aluminum hydride. Capable of adding to this carbon, kicking the lone pair over there, and that's where we have our R, CH2, H2. And so essentially the idea here is that nitrogen less likely to go without the presence of water. That this aluminum oxide compound can then be neutralized by adding water and precipitating that out. So we can do reactions with organometallics, so let's not forget those. That's where we started this year off, learning about organometallic reactions. So don't forget those. Esters and acids, acyl chlorides, will react 2 times with our base grignards and our organolithium. So CO2R and RCOCl plus 2 equivalents of our RMGX or RLI. I'm going to add first to the carbonyl, kick that down, and then reform our carbonyl as we kick off the leaving group. And then do it again because we still have that aldehyde peak. So still going to keep reacting with these strong, these very basic nucleophilic groups. We already saw this, but I'll just show it again just to make sure we got ester. Okay, organolithium, R double prime. So this is a minus, this is a plus, is going to go, oh, we're going to attack here, kick that up. So we have R, C, O, we'll just say O lithium, O, R double prime, well, actually, that's single prime. There's our R double prime. So swing down, kick out our functional group. Reform our aldehyde. C double bond O. Then we add again. And of course, finally, last step is add water to form the alcohol. Li, going to form our C. Water neutralizes the remaining organometallic and forms our tertiary alcohol. This mechanism already kind of gone over, but just feel like sharing that just to make sure. Water, acid, typically acid, it's fine. So now acyl chlorides are special because acyl chlorides, due to the reactivity, we can, using a special catalyst, a special reactant, only add one equivalent. Remember this guy? This would, if that was the Grignard and the organolithium, this was a Gilman reagent, if I'm not mistaken. The Gilman reagent was essentially this, and we say RCl. Essentially, the Gilman replaced just the chloride. It doesn't attack the carbonyl. I mean, it does attack the carbonyl, but it doesn't keep attacking the carbonyl. It will only replace that chloride. Essentially, there's a way to just form a ketone. Ah, jeez. Nitriles. Nitriles will form an imine, which can be then acidically hydrolyzed to a ketone. So these guys were also reactive with organometallics. You can do, oh, prime R N minus. And then if we react it with sufficient acid, first we're going to pronate the imine. If we keep reacting, remember we we can kick that off and form our ketone and ammonia. So keep reacting. So those are all the just generalized reactions that we're going to look at. Now we're going to start to look at individual reactions for each guy in turn. A lot of these are going to be like some review. A lot of these are going to be like, oh, hey, we've seen these before. We've seen these before. So it may be a lot of reactions, but it's just building on what we just kind of went over. Just making sure to, instead of just look at a whole swath, we're going to narrow it down and look at individual ones. So we'll start with acid chlorides, and so we'll see how far we go. First thing is, how do we form acid chlorides? We've seen this before, seen this reaction before, but we gotta hit it again because this is key way we form acid chlorides. We form acid chlorides from carboxylic acids. We either use our thionyl chloride is one option, or oxalic chloride, or it's the C double bond O, C double bond O. But either one of these would, where essentially we're kicking this off, forming our acid chlorides and some gases. Kind of want to, so either forming SO2 or CO and CO2 and HCl. Either way, as we lose them as gases, we're kind of left with our, it like forces this to products, and thus we can keep this where we want. Now, why is this such a good reaction? Why is this so important? Because this is so very reactive. It's so easy to form our intermediates with high amounts of yield. And so all these are going to be from the starting point of acyl chloride. So just a quick reminder, if I acyl chloride in water, gotta be careful. You're going to kick this right back to an acid. So that's not super helpful. And most of these guys will have hydrochloric acid as our byproduct. But say you could use the SOCl2 to turn something else into it. But so we got to prevent water from contacting this. If I use an alcohol, really easy, really convenient way to make an ester. If I use any sort of amine, really convenient way to make an amine. If I use another acid, another carboxylic acid, really convenient way of making it an hydride. All these groups are going to attack and displace the chloride. You've covered all these before, except for maybe that water one. Some of these, again, I'll erase. Because we got more reactions. So all those we've really covered before. So just our basics of how do we form any of those groups once we have these acyl chlorides. You just mix it in. It's like bam, wham, bam. reiterate, we could do organometallics, either RMGX or R lithium. Two equivalents, water, acid. You're going to form our tertiary alcohol. I use the Gilman reagent. When we take the organolithium and mix in copper, we're going to just form our ketone. If I use either lithium aluminum hydride or sodium borohydride, because this is so darn reactive, plus water. Second step, we're going to form a primary alcohol. And finally, if I use the specialized lithium aluminum hydride tert butoxide, which is essentially going to be a sterically hindered version of this, I can form an aldehyde. So those are all ones we've just covered. So as I said, before you go, oh, my head, that's too much to learn. All of those are ones we just covered. I'm just reiterating reactions we've just done over the last couple classes. Just a reminder of, oh, look at the practicality and applicability of this. Now, this is another one. The last reaction, and this is one we've also covered, not anything new. Friedel-Crafts Isolation. So, FC acyl. What was that? Our acid chloride plus some sort of benzene, some sort of substitute benzene. As long as it's ortho-para substitute, we used aluminum trichloride and then water to help kick it off at the end. We're going to have some ortho-para substituted benzyl ketone. So all this was known. So Friedel-Crafts Isolation. So all those are some of the many reactions of the acyl chlorides, or acid chlorides. Now, look at the chemistry of anhydrides. Anhydride is very reactive, but not nearly as reactive as our acid chlorides. How do we synthesize this? Easiest way to synthesize this is, once again, from the acid chloride. So just reiterate this. That's our basic starting point. We have acid chloride, we mix in. It doesn't have to be the same R group. It can be a different R group. We mix together some sort of acid or carboxylate, and we form our byproduct. So there's our acid chloride. So let's look at some interesting reactions. First things first is there's other ways to make anhydrides, and that is using diacids. So if we have a diacid of any kind, as long as it's significantly overly, with it 1, 2, 3, as long as it can make essentially a a 5-membered ring, it can be very stable. So this is what, like 1, 2, what, benzene dioic acid, or benzoic, 1, 2 dibenzoic acid, or benzodioic acid. Just adding heat will cause us to cyclize and dehydrate into a stable bicyclic ring. But it doesn't have to have a benzene. We could also so that one's very stable, it just needs heat. This guy needs a little bit of help, but with a mix in ethyl acyl chloride or ethanoyl chloride. I can deprotonate that with ethanoyl chloride. Actually, dehydroxylate that. Ethanoyl chloride and kick that out to form our 5-membered cyclic anhydride. And this forms carboxylic acid. But both of these guys are relatively stable. Now, looking at anhydrides. Some of these guys are going to be repetitions of stuff we already know. So we're going to do a symmetrical anhydride just to avoid extra confusion, because we could go either way. It could attack either functional group and thus get 2 products unless it's symmetrical. So water, so reactive that we mix in water, you're going to get 2 equivalents of the carboxylic acids. If I mix in alcohol in the presence of acid, so we didn't have to add that acid when we added the acyl chlorides. But we're going to get a carboxylic, what? We're going to get an ester and our carboxylic. And if we do an amine and we do amine NH2, we get an amide acid. Of course, this case, the amide is our, it's enough of a, like, more willing to give up that proton. Now, all those are, well, we already kind of covered those. Those aren't really anything new. We could also, here's something new, is that we can, much like acyl chloride, we can also do a Friedel-Crafts Isolation with this guy. Almost identical conditions. So really, actually, quite quite identical. These are such good leaving groups. Don't have any problem. You can just do this with. We have our benzene. We have some sort of our substituted benzene. And we have step 1, we use our aluminum chloride. Step 2, we use our water. Now, I think I have something else down. I think there's another functional group we could use as well. Okay. So you can use aluminum trichloride, or you can use other acidic catalysts. So we don't have to use aluminum trichloride. We could actually use, I think, they say polyphosphoric acid. Polyphosphoric acid, and you would essentially form a acyl group onto there. In fact, we can use our cyclic anhydrides, and they will ring open to add onto there. And you can use that with aluminum chloride. Kind of interesting. Essentially, it's going to be, oh, we've ring open it. A useful way of adding more functional groups onto there. But, okay. Most anhydrides will lose an acid as a leaving group. Now, acetic formic anhydride will donate the whole formyl group. That as this guy is a stronger reactant than this guy. But that's just a quick summary of our anhydride reactions. Our esters, just review our esters real quick. Esters are compounds that are responsible for all of our good smells. I'm not gonna, I mean, there's many ways to synthesize esters. So let's look at them. Most of the time, our esters are formed from a starting alcohol. And most of these guys are reversible. So if I do in the presence of an acid, carboxylic acid, proton, I can possibly force this to completion. Oftentimes water is a byproduct. In this case, water is a byproduct of H2O. If I do with acid chloride, I can do it irreversibly. Acid chloride, form HCl as a byproduct. If I do an anhydride, sorry, and hydride, we're going to form like another case where oh, another case that's not really reversible. Or we could do this as trans-esterification with another ester in the presence of either an acid or a base. All of these are ones we've covered, so they're not really anything new. They're just iteration. There's one other way we can make an ester, and that's with our diazonium, methyl-diazonium. So we could do this with CH2N2 and mix that with a carboxylic acid. Once again, we have this is good because it forces this to completion as we were losing nitrogen. Yes. Now, the generalized reactions of esters, these are going to be even less reactive than our acyl chlorides and anhydrides. They will need either an acid or a base as a catalyst. But that can be in the favor because that means remember, these guys are going to be then more stable. They're not going to just, whoops, I left this out on the counter too long. Water's gotten into it from the atmosphere. It is now deactivated. So water, most of these are reversible, but just to save time, I'm going to reversible arrow out. Presence of water, well, form carboxylic acid. Of course, an alcohol. In the presence of another alcohol, we just kind of did this one. Acid or base. Transesterification. So don't forget, you can always reverse this easily enough. You just put the alcohol you want in excess. I can use amine. This one doesn't actually need acid or base. Amine is going to be a good leaving group. I mean, the amine is going to have a good proton. The amide is going to donate that proton easily enough. Erase those. So those three. Look at that. Save myself some trouble. Leave that. Okay. Let's look at this, guys. Okay. We could also go with the lithium aluminum hydride, remember. Step 1, step 2, water. form alcohol and another alcohol. Fully reduce that. I use 2 equivalents of Grignard or organolithium. I'm going to just save my hand by not writing organolithium. And this is a strange one, the diisobutyl. So we call it DIB aluminum hydride. Diisobutyl aluminum hydride at -78, followed by thin water. We can manage to get to aldehyde. We've all covered these guys. Now there's one other reaction we can do with this, and that is if I have an alcohol and an alcohol and acid in the same compound, we can form a cyclic lactone by acid hydrolysis. It's just that's a form of cyclic ester. Okay. All those are examples of our ester reactions. So we're going to try to finish. So we'll go ahead and start amides. So synthesis of amides. These guys are the least reactive, thus the most stable of all of our compounds. So we can form these guys, remember, from acids and amines, by just adding heat to dehydrate these guys. So like 300 degrees, for example. We'll form an amide. And water. This is how they usually do it on industrial scales. Not always as practical for us in the lab. Maybe a more practical one would be our acyl chloride. Just to reiterate, we actually probably have to add 2 equivalents because we're going to from ammonium chloride. Usually say it's just acting as a base. We can react these with, we can react these with acid and hydrides. So, each forms are, of course, our amide and our acid. can use esters to make them from esters. All these are just reiterations. As long as they are more reactive than our starting point, or more reactive than our ending product, it's easily enough done. Essentially, what we're saying. Always react in one direction until you put the right reactant to put it back. It's going to be going down the slope until you take the chairlift all the way back up. And of course, we can make them from nitriles, as long as you're very careful not to over react and knock them to carboxylic acids. I think base might be the best way to make these to prevent. We can go from nitrile to amides. Can't make a substituted amide that way. So all those are just a quick reiteration of all the reactions we have seen to form amides. All these we've seen. I don't feel like not including this because it's like a good summarization of everything we've covered. Good summarization. Now, as we react these guys, amides are not very basic. This is because we, due to the resonance, or essentially we would lose resonance if they were to become protonated. So it's not very stable. Now, protonation can occur, but it requires a strong acid. And actually, when we protonate these amides, they're going to protonate on the carbonyl group rather than on the amide, the amino group. That is because we can still keep the resonance structure if you protonate the carbonyl, but we lose any hope of resonance the second that amine gets protonated. Now let's look at some reactions. There's really not nearly as many for these guys. So, because once again, we get less and less reactive as we go down. If I have amine, I react with water, presence of acid, base, force this back to a carboxylic acid again and a amine. If I use lithium aluminum hydride, water, I can force this to a primary amine. And the only one that's really new that we didn't spend a lot of time on is a way to go from amide to nitrile, which is it's a phosphorus oxide trichloride or diphosphorus pentoxide. Both of these are strong. Let's see. Oxidants, I'd like to say, but they remove the oxygen part of there, and then we're just increasing the number of bonds to carbon nitrogen. So we essentially remove that oxygen, removes any of the hydrogens attached to the nitrogen, but that only really works with primary amides. Now, POCl3 and P2O5 are really strong dehydrating agents. And so those are going to be the easiest way to make a nitrile from an amide. It's really easy to go from amide to nitrile with just water. remember, water, essentially acid or base, will turn it to an amide and then maybe even to a carboxylic acid. Well, by dehydrating the water out, we can form them into a nitrile. So, and the last reaction talk about for amides would be formation of lactams. That small lactams can form with heat by dehydration. Same way we had lactones. One, under the presence of heat, we'd have water, or so we can make cyclic lactams by reacting amine with acid. So we have a few more reactions to cover. I'm going to go ahead and plow through and finish this off so I can finish the chapter. Then we'd only have one more chapter to go. So this is just the reactions of nitriles. It's not very much. Not very much. So how do we synthesize nitriles? Well, the first one we just covered, using an amide and our strong dehydrating agent, like POCl3 or P2O5. We'll force this to. Now we could also make our nitriles from chlorides that we can kick off using sodium cyanide. And that's going to essentially just become a nucleophile and kick that off. And so we have nitrile. That requires you to already have a nitrile. And of course, we could do this with a diazonium using copper. We kind of covered this chapter or so ago. Kicks off dinitrogen. And we could do this with a ketone. This makes a hydrocyanin, HCN, and then KCN. Pronate the ketone and add the cyanide to the other side. So those are just ways to form cyanide. There's not ways to form nitrile. There is not a whole lot. Now the reactions. There's also not a whole lot of reactions. So we'll limit it to these 4. So nitriles, in the presence of water, acid or base. We can first go back. We'll first go back to an amide, but allowing to keep. If we allow it to keep reacting, it will eventually go back to a carboxylic acid. Using lithium aluminum hydride. Water. We're going to go to a primary amide or primary amine. RCH2 and H2. Using a Grignard. And depending on what conditions we do, we could either stop this as a mean or can go all the way back to go to a ketone. So essentially we go, oh, this is the intermediate. In the presence of acid, though, in the presence of acid, then we can kick out the ketone. Oh, wait, kick out the imine and form a ketone. And then finally, the last reaction is using one of our fancy weak reductants, the diisobutyl aluminum hydride at negative 78 degrees C, and then acid, possibility to, again, put it into an aldehyde. Probably goes through an imine intermediate, and then we remove the imine and replace it with the oxygen. So those are all the reactions we're going to care to cover for nitrile. We're going to go ahead and skip. There are some more reactions in this chapter, and we're just not going to cover them. It's already a lot. We're going to skip thioethers. We're going to skip carbamates and carbonate, and we're going to skip carbonates. We're going to skip urea. All these great ones with crazy different combinations of not multiple nitrogens and oxygens. We're not going to worry about them too much. We're not going to worry about them right now. We got enough on our plate. So that is all the reactions, like finishing off chapter 21, which is carboxylic acid derivatives. Completely finished. The last chapter we will cover this year is 22, which is condensations and alpha substitutions, which is a whole lot of the reactions that essentially that use ketones, but where ketone isn't the actual reactive portion. It's how we form a lot of different combination products where we stick this onto there and increase the chain length. That's where we're going to end up on Wednesday. So once again, if you found this interesting, please like, please subscribe, and I'll catch you on the flip side.